Hello and welcome to the presentation of our paper. My partner Luz Natalia Hernandez and myself, Enrique Lugo, are going to be presenting the paper titled Smart Temperature Sensors based on flexible carbon black, thermoplastic polyurethane, and polyvinylidene fluoride membranes for eliminating pressure interference. Thank you for listening.
This study takes the challenge of signal interference in flexible temperature sensors. It was proposed a solution-based method in TPU, carbon black, and ionic liquid TFSI. This incorporated into a PVDF to form a flexible composite capable of sensing both temperature and pressure. This resulting sensor shows an improved conductivity, enhanced interfacial stability, and stretchability up to 375%. It performs reliably in human motion tests and with machine learning and PCA. Pressure interference can be effectively removed, reaching 98%. Flexible sensors are getting attention because they adapt well to complex surfaces and offer advantages for health care, soft robotics, and others. Flexible temperature sensors work by using materials whose electrical behavior changes with temperature, but many polymer-based systems losing sensitivity at higher temperatures due to swelling that disrupts conductive pathways. Recent strategies using hydrogels, carbon nanotubes, and PVDF composites have improved performance to issues with thermal stability and pressure interferences persist. Because materials like PVDF also respond to pressure distinguished through temperature signals remains challenging. This had led to increasing interest in mathematical and AI-based methods to separate mixed signals and improve temperature sensing accuracy. The TPU PVDF DFSI CB membrane was prepared using a simple solution blending method. TPU and PVDF were dissolved in DMF, then carbon black and the ionic liquid TFSI were added to form a uniform composite solution. This mixture was laid coated onto glass to create a 70 750 micrometer film dried in a vacuum oven and trimmed for uniform thickness. Finally, silver adhesive electrodes were attached on both sides of the membrane, completing the fabrication of the temperature sensor.
Thanks, partner. To rigorously validate this sensor, the researchers moved beyond simple functional testing to investigate the underlying physical mechanisms. The characterization strategy presented in this paper is structured into four distinct pillars shown in this slide. First, the structural analysis, focusing on molecular interactions and crystallinity to explain the material's stability with FDIR and XRD. Second, the morphology and composition. So visualizing the porous network and verifying the homogeneity of the mixture. Uh, in the third part, the mechanical and physical properties. So defining the operational limits regarding flexibility and stability. And finally, the functional performance where the signal itself is analyzed. And lastly, as noted at the bottom of the slide, the study utilizes data characterization via machine learning and principal component analysis. So this computational step is treated as a distinct characterization technique to interpret the complex signals and achieve the smart decoupling capability. So I will guide you through the material characterization, which is the structural, morphological, and mechanical findings before passing it back to my partner for the functional sensor analysis. Let's begin with FTIR. So, to evaluate the chemical compatibility of the components, the composite membrane was prepared using was prepared and tested using a nickel IS-10 spectrometer. The spectra shows the composite membrane of ratio 1:1 for the black line, 2:1 for the red one, and 3:1 for the blue one. The attention should be drawn to the spectra on the left. Uh, this analysis focuses on band shift rather than just a band presence, as these indicate intermolecular interactions. Specifically, looking at the nitrogen and hydrogen stretching band at 3,323 inverse centimeters, and the carbonyl, so carbon double bonded with oxygen, band at 1,725 inverse centimeters. So distinct changes are visible in this case. In the material composite, this band shift to slightly higher wave numbers, so 2 or 3 wave numbers respectively. So the significance of this result is high because these shifts are identified by the authors as the definitive fingerprint of hydrogen bonding. It demonstrates that the TPU and the PUVDF are interacting at a molecular level. So this molecular glue is what provides the sensor with its structural stability under thermal stress. Moving on with X-ray diffraction, this was utilized to determine how this blending process affected the polymer's crystal structure. The films were scanned from 10 to 70 degrees of the theta. If you look at the red line, which represents the PUVDF, the indexed peaks characteristic of the alpha and gamma crystalline phases are visible for the PUVDF. In comparison, the orange line, which represents the composite, shows a significant change. The characteristic gamma phase peak at 38.8 degrees has almost completely disappeared. So the key takeaway from this data is that the incorporation of the TPU physically disrupted the orderly arrangement of the POVDF chains. This resulted in reduced crystallinity and an increased amorphous region. So this structural change is critical as a more amorphous structure translates directly to the higher flexibility and stretchability reported later in the study. Now, to verify the physical microstructure, SEM was performed. The samples were coated with gold to prevent charging and imaged using a Quanta 250 SEM. But normally, when looking for microstructure, the images are obtained with secondary electrons. The images on the left demonstrate the evolution of the microstructure as the ratio of TPU is altered. In image A, at a ratio of 1:1, a highly porous sponge-like network is observed. The authors attribute this porosity to the presence of the TFSI ionic liquid during the solvent evaporation process. However, as the TPU content is increased, as seen in images B and C, this network becomes denser. This characterization is vital for explaining the sensor's mechanism. The purse network functions effectively as a spring when pressure is applied. These pores compress, altering the conductive pathways. Without this SEM confirmation, the physical driver behind the pressure response would remain somewhat theoretical. Next one, a porous structure is only effective if the conductive elements are correctly positioned. Therefore, the SEM was coupled with the EDS to map the elemental distribution. The analysis specifically tracked sulfur and nitrogen, which serve as the unique markers for the TFSI ionic liquid. So this shown mapping is only for the ratio 2 to 1 of the membrane composite. So observing the maps on the right, specifically the bottom row, a uniform homogeneous distribution of this element is evident across the entire field of view. There is no significant agglomeration or hotspots detected, and this confirms that the solution blending method was successful. The ionic liquid is evenly dispersed throughout the polymer matrix, ensuring that the ionic conductivity, which uh, this is consistent across the entire sensor area. Now, finally, to validate the material for potential wearable applications, tensile stress strain analysis was conducted using a universal testing machine. The standard rectangular specimens were prepared and stretched to the point of failure. The graph on the left illustrates the flexibility profile. The composite with a 1-to-1 ratio appears to be relatively rigid. However, as the TPU content increases, represented by the teal line for the 5-to-1 ratio, a substantial increase in strain capability is observed. So this study achieved a maximum elongation of 420%. So to put this in context, human skin stretches approximately 20 to 30%. So this sensor demonstrates an ability to stretch over 10 times that amount without mechanical failure. This characterizes the material as robust and enough to withstand the mechanical stresses of human motion, such as finger bending, which was a tired application. So, having characterized the material as a stable, porous, and homogeneous, and highly stretchable composite, my partner will now explain its physical performance in wet environments and the methodology used to decouple the signals.
The water contact angle of the samples was measured using an optical contact angle device, and tensile properties were evaluated using standardized specimens tested at room temperature. As the TPU content increased, the water contact angle also rose, indicating higher surface energy and weaker van der Waals interaction at the surface. This change improves the humidity stability of the temperature sensor. So for the functional testing, the electrical response of the TPU PVDF TFSI-CB sensor, the samples were primed and picked with silver adhesive electrodes, then tested using a Kitley 2400 under a constant 10 volts base. The device was supposed to control heating from 35 to 85 degrees Celsius and pressures from zero point 0.1 to 2.44 kilopascals. The results confirm dual sensibility, a temperature sensibility of about 1.24% per degree Celsius, and a pressure sensitivity of 0.17 per kilopascal. The plots illustrate consistent stable responses across both temperature and pressure. 10 samples were extracted from the electrical response curves, including S max response in area, and Gaussian noise was added to expand the data set and improve variability. After that, principal component analysis was applied to reduce the original 10-dimensional data into two principal components. This transformation created a clear separation between temperature and pressure signals in the 2D space, forming non-overlapping clusters and enabling a classification accuracy of 98%. As a summary, it was developed a flexible PVDF base membrane enhanced with TPU, TFSI, and carbon black for dual temperature and pressure sensing. TPU greatly boasts stretchability and temperature response, and the sensor works well for human motion monitoring with machine learning. It self calibrates and separates temperature signals with high accuracy.